Alright, so I'm going to title this video "So You Really Wanted to Go Down That Road." This is not part of what the book does, but some of you might want to see partial fraction expansion if you have complex roots. So let's just start with this one. 1 over s squared plus 2s plus 2. And I've used this example again. If we want to calculate the roots of this, we get two complex roots. But how do we find those roots? No, well, let's just say s squared plus 2s plus 2 equals 0. I get s1 and s2 is minus b, so minus 2 plus or minus the square root of 4 squared minus 8. It's minus 4 over 2, and we find that this is minus 1 plus or minus j. So we found our complex roots, which means that I can write s squared plus 2s plus 2 as s minus s1 times s minus s2. So we can factorize this with our complex roots, which means that if we really want to, we can write this as a over s minus s1 plus b over s minus s2. Now keep in mind that if we were to use the technique of completing the square, and I'll just write that below here, we could write this as 1 over s plus 1 squared plus 1. And if we wanted to take the Laplace the inverse Laplace transform of this, this would even already be in the table, and we get e to the power of minus t cosine of t. So this is the work we have to do with completing this square. Now, you really wanted to go down that road. All right, so first thing we have to do is find a and b. So we do it the same way as we did before. We multiply. So let's just rewrite this out. So a over s plus 1 minus j plus b over s plus 1 plus j. So this is if we rewrite this in terms of our two complex roots. Now we have to find a and b. So we rewrite this as a times, a over s plus 1 minus j times s plus 1 plus j over s plus 1 plus j plus b over s plus 1 plus j times s plus 1 minus j over s plus 1 minus j. Like we did before, but now we have complex numbers, which makes it a whole lot more annoying. All right, that is equal to as plus a times j plus bs plus b minus b times j over s plus 1 minus j s plus 1 plus j. And we know that this will end up being s squared plus 2s plus 2. So after this, I will rewrite it like this. So we have a plus b times s plus a plus aj plus b minus b times j over s squared plus 2s plus 2. So this was just the factorization of this, so I can write it like this. So now this expression has to be equal to that. So we get a plus b times s plus a times j plus b minus b times j is equal to 1, which means the coefficient for s must be equal to 0. So a plus b is equal to 0. And we get a plus a times j plus b minus b times j is equal to 1. Well, from the first expression, we know that a is equal to minus b. So minus b times j plus b minus b times j is equal to 1. These two cancel out, so I have minus 2b is equal, sorry, b times j is equal to 1. And that means that b is equal to, what do we have? 1/2 times j. Because if I have the minus 2 times the half, I get minus 1. The j times j squared is minus 1, and I end up with my 1. And this altogether makes that a is minus 1/2 times j. So we have our factorization. Minus 1/2 j over s plus 1 minus j. I don't know why I keep writing a 9. Plus 1/2 times j s plus 1 plus j. And it's really clear that this is, we're not quite ready yet to put this in a Laplace transform. But we're not too far off. So I want to rewrite this again in the form of my Laplace transform, that the Laplace inverse of 1 over s plus a is e to the power of minus at. So this is the one I'm shooting for. So minus 1/2 j times 1 over s minus, or s, I can write this as, like this as well, 1 minus j plus 1/2 j 1 over s plus 1 plus j. And here I can take the two Laplace inverse. So the Laplace inverse of our original expression, 1 over s squared plus 2s plus 2, is equal to, well, minus 1/2 j e to the power of 1 minus j times t. And I've lost the minus sign here, plus 1/2 times j e to the power of minus 1 plus j times t. And this still doesn't look like a function we can do anything with. But we can rewrite these exponentials, because we know that e to the power of a times b, a plus b is e to the power of a times e to the power of b. So that's the first thing we're going to use here. Is I'm going to just take this minus 1/2 j, and then write e to the power of minus 1 minus j times t plus, sorry, minus, because I've got a minus there, minus e to the power of minus 1 plus j times t. So this is just rewriting this expression. Now I'm going to use this rule, is minus 1/2 j times e to the power of minus t, e to the power of minus times minus is plus jt, minus e to the power of minus t, e to the power of minus jt. And again, you wanted to go down this road. I'll take this e to the power of minus t out of the brackets, so we get minus 1/2 j e to the power of minus t times e to the power of jt minus e to the power of minus jt. And this should be something where we are slightly more familiar, because we also know that e to the power of jt is cosine of t plus j times the sine of t, and e to the power of minus jt is cosine minus t, but because cosine is symmetric, we get cosine t plus j sine of minus t, but that is equal to minus sine of jt. And if we take the top one and subtract the bottom one, what we get is minus 1/2 j e to the power of minus t times, well, the cosines cancel out, and we are left with 2 times j sine of t. We're almost there. So the 2 and the half cancel out. So this is minus j e to the power of minus t times j sine of t. I multiply minus j by j, which is minus 1. So the minuses cancel out. So we've got e to the power of minus t times sine of t. So we needed all this work instead of simply writing it as the in the form where we use completing the square and looking it up. Oh, yes, and of course I made a slight mistake here. This is not cosine, this is sine. Sorry about that. So by completing the square, we can more or less write it out immediately. If we really want to do partial fraction expansion with complex roots, yes, we can do it, but why? This is just, this is too much work for something that we can do a lot faster in a different way. So if you really want to go down that road, fine, but I would recommend using completing the square.